Okay, here's our video for energy in space. All right, so we've done this whole topic for energy in space, or for energy. We've done conservation of energy, looked at work, the different types of energy, power, most recently, collisions, all those kinds of things. But now, energy in space, this is our last topic for this. We know, right? We know that energy initial plus work equals energy final. And we just know that that's just a fact of life. It has to be that way. It will always be that way. This is one of really our two guiding principles of physics. We have that conservation of energy and conservation of momentum. That's it. Period. End of story. So if we have something that is just moving on its own, it has to start with some amount of energy and finish with the same amount of energy unless some sort of work is applied to it. Remember, that's plus or minus that work, depending on if we put energy in or we took energy out. Either way. Okay, but let's look at this in the context of space. The context of space, right? As we're in space, and we've talked about this with circular motion so far. Right, we have, let's use orange for the sun. Perfect. There's orange for the sun. Don't mind my cat feeder going off in the background. Sorry about that. There's orange for the sun. Let's say this is the path of some planet around the sun. Pretend that's an ellipse. Right? Kepler's first law tells us that in space, a planet will orbit around the sun with the sun at one of the foci, or one of the focuses of that ellipse. Now, there's some other focus right over there, right, symmetrical to that, but nothing exists there. Let me redraw this ellipse, maybe make it a little bit better. There we go. Okay. So, right, what's cool about ellipses is we know that over here, that's the closest that it will ever get to the sun. And pardon my bad drawing. I know I didn't draw that necessarily the best. I can move the sun in this. Here we go. Okay, that's maybe more what it would look like. The sun, that's the closest it ever gets to the path of the planet. But then the furthest it ever gets to the path of the planet is all the way on the other side. Well, all right, let's think about this though. What kind of energy is happening here when we get farther from a gravitational source? When we get farther from a gravitational source, we are going to increase our gravitational potential energy. And then when we get closer to the gravitational source, right, we're decreasing our gravitational potential energy. Okay. And then right in the middle, right, we'll just have something right in the middle when we're about halfway in. But if we have the greatest gravitational potential energy over here, and then when we get closer, we decrease our gravitational potential energy. Remember our equation, potential energy of gravity equals mgh. Now this doesn't truly apply the same because this g, right, that g, that's 10 or 9.8 if you're going to be precise, but we've used 10. That g only applies on the surface of the Earth. So that's not quite going to be exactly the equation, but we can just say for the purposes of this that it depends on h. Right? If we were to look at this all through this lens, and what we see actually, right, the acceleration of gravity at any point, g is big G times the mass of that thing over r squared. But whatever that radius away is, if we want to take this potential energy of gravity and we want to get the real number, we can take that over there and say the potential energy of gravity in space for anything is the mass of our little object times g m over r squared, right? That's acceleration of gravity times h. That's the distance away. But what do we know about this height? right? The height is the same thing as the distance r squared. So what we'll actually do is call that r. What this means then, right, one of those r's on top cancels out with, or the r on top cancels with the r on the bottom, but the potential energy of gravity is just g, mass of the sun, mass of whatever's rotating around it, over r. This is what we get for anything in space. So potential energy of gravity is equal to gmm over r. Not squared, just r. All right. So that's our equation, potential energy of gravity. Remember, AP writes all potential energies as mu, so or as capital U. Sorry, capital U. So if we're ever going to write this, it's capital U equals gmm over r, and that's what AP will give you. Okay. So now that we kind of know that, we can look at, well, what happens as we move around, right? As we move around our ellipse here, let's say we're orbiting this way. As we move around our ellipse, right, our potential energy of gravity is at its maximum here, and then it decreases as we get closer and as we get closer. Potential energy of gravity decreases as we get closer and closer. Okay, but what that means is, what does it turn into? We know that this equation up here must be satisfied. Our energy initial equals energy final, and in space, there's not going to be a work term. There's not going to be a work term in space. So what does that all turn into? An increase in kinetic energy. So right over here, this will be our decrease in kinetic energy. But then over here, it's our increase in kinetic energy. Okay. So that's actually, if you remember, Kepler's second law. Kepler's second law explains to us that in equal amounts of times, an object will sweep an equal area. All right, so Kepler's second law will say that an equal amount of time, right, our planet will go through that, and the planet will go through that. When the planet is closer, right, it moves further in the same time, versus when it's farther, it moves less far. So this basically means it's moving slower. It's moving slower over here. Velocity is low, but then over here, velocity is high. That law, Kepler's second law, is explained by the conservation of energy. When we decrease our potential energy of gravity, it has to turn into something else. It turns into kinetic energy. Okay. Oh, I forgot to mention. Sorry, I'm going to come back to this potential energy of gravity here. What this truly is we get a negative sign. We get this negative sign, negative gmm over r. What this tells us, right, is if we increase our radius, we know that we should be getting more potential energy of gravity. But if we didn't have that negative sign, increasing r, increase the denominator, would give us a smaller number. And having a little r would give us a bigger number. But we know that has to be opposite. We know that has to be opposite. So what we do is this equation right here with this negative sign, that means that the largest potential energy of gravity for something in space can ever get is 0. The largest it can ever get is at, so potential energy of gravity, right, the max equals 0 joules, and that's when R is infinite. Right, when I'm infinitely far away, that means, like, let's say I'm infinitely far away from the sun. That means that the sun is not exerting any gravity on me. I have no potential to move toward the sun. But as soon as I move just a little bit closer, the sun's going to exert a gravitational force on me. And right there, that's a potential for it to move me closer and change that into kinetic energy. So as potential energy decreases, kinetic energy increases. But to make it decrease, we have to have this negative sign. That negative, all that negative means is that in space things attract. They want to get closer. So that's truly what our equation is there. Okay. Hopefully you understood my scribbles well enough. Let's take a look now. Let's take a look now at these questions. So these are questions straight from AP, exactly the kind of thing that you might see. So in the picture above, we have a spherical satellite. That's this little ball here is shown at point A, orbiting the Earth in the clockwise direction. So it's orbiting Earth in the clockwise direction. Okay. Orbiting Earth clockwise direction. The dashed line represents a circular orbit, and the solid line represents the actual path of the satellite. Okay, so it's moving out here. Okay, how does the total energy of the satellite compare between points A and B? Circle 1. Right? Well, we know this relationship. E naught plus work equals E final. Is anything exerting work on our satellite as it's moving around the system? No, it's all just the satellite and the Earth. Those are the only things changing, or those are the only things doing anything, moving anything. So that means there's no work. What does that mean about energy initial and energy final? It stays the same. Okay, how does the gravitational potential energy of the satellite compare between points A and B? Does it increase or does it decrease? Well, at point B, how far away are we? Basically, right? What's our height? It's that far, but at point A, oh, it's only that far. That means we have a larger height at point B, so our gravitational potential energy will increase from point A to point B. Okay. As a result of parts A and B combined, how does kinetic energy change between point A and point B? Right, I know my energy at A has to equal my energy at B. Right, I know that must be true. Energy at A, well, I have just a little bit of potential energy of gravity, but energy at B, I have a lot of potential energy of gravity. Now we know there has to be some kinetic energy as well, but since my potential energy got big, that means my kinetic energy had to get small. So conversely, on the other side, the gravitational potential energy got small. What does that mean about kinetic energy? It has to be a big number to make sure that happens. Okay, so how does kinetic energy compare between point A and point B? Well, from A to B, kinetic energy, it went from fast, right? When it's close, it's fast. When it's far, it's slow. So from point A to point B, kinetic energy decreased. All right, write the equation for the total energy of the satellite at point B in terms of the types of energy that exist there. Well, we kind of just did this. Energy at B total, right? That'll have a lot of potential energy of gravity because it's far away. However, it also has a little bit of kinetic energy, right? Because if it didn't have kinetic energy, it would just be stopped. That's all it would do. Is it would just be stopped right there. And when something is stopped and in a gravitational field of something, what happens? It just fall right in. So it has to have some sort of kinetic energy, so it doesn't do that. So it continues. So it continues around this path here. All right. Oh, I'll erase these arrows that don't mean anything. There we go. Okay. The satellite is moving at 3,000 meters per second at point B. If point B is 12,000 kilometers above the Earth's surface and point A is 2,500 kilometers above the Earth's surface, how fast is the satellite moving at point A? Okay. Well, 12,000 kilometers, remember that's going to be 12 million meters, right? Times 1,000, and then 2,500,000 meters. How fast is the satellite moving at point A? Okay. So we know, right, we established earlier the energy at A has to equal the energy at B. It just has to be equal to that. So at A, right, we have kinetic energy at point A, and there's some potential energy of gravity at point A. And then, right, that has to be equal what we have before, potential energy of gravity at point B. plus that kinetic energy at point B, whatever that is. Okay, so we know 1/2 mv squared, that's velocity at A, plus, oh, and this is our potential energy of gravity. We are in space. We are in space, so we have to use this equation that we were talking about earlier. We have to use that equation there. Negative GMM over R. We have to use negative G, big mass, little mass, over R. Remember, the big mass is what is it orbiting? Little mass is what is doing the orbit. Okay, and that's radius at point A. Then potential energy of gravity, point B. Well, it's the same equation. G, mass that's causing the orbit, mass that's doing the orbit, over the radius at B. And remember that negative sign, plus 1/2 mass VB squared. Okay, well, what can we do? What can we do? We can cancel out the mass of the satellite, right? The satellite mass is in every single term, the thing that's doing the orbit. Okay, so now what we get 1/2 times the velocity at A squared, plus we get negative, and I'll start filling in numbers, 6.67 times 10 to the minus 11 times mass of the Earth. Mass of the Earth is 6 times 10 to the 24th kilograms. I don't expect you to know that, but I know it off the top of my head because I've just seen it so many times. Over radius of A. How far away is it at point A? 2,500,000. 2,500,000 meters over R. Okay. And remember, this isn't over R squared, it's just over R because we had to multiply, right, MGH. Okay, but then equals, similar thing, negative 6.67 times 10 to the minus 11. Mass of the Earth, 6 times 10 to the 24th kilograms, over, this one's massive, or sorry, the radius RB, distance away from point B, 12 million meters. That's the same as 12 times 10 to the 6th meters. Plus 1/2 velocity of B. Well, velocity of B, so it's 3,000 meters per second at point B. So times 3,000 squared. Okay. Let's do some math, shall we? Let's do some math. Turn my calculator on, maybe. Here we go. Okay, let's just do this one term at a time. 6.67 times 10 to the minus 11 times the mass of the Earth, 6e24. Oh, I missed a 1 earlier on the 11. Insert 11 times 6 times 10 to the 24 divided by 2,000 or 2,500,000. 2,500,000. So that gets us, that one is, oh, let's see how many decimal places. 1, 2, 3, 4, 5, 6, 7, 8. Okay, so we have 1/2 velocity of A squared equals 1.6, is it 008 times 10 to the 8th? And that was minus sign there. Sorry about the equals. Minus that equals, okay, now we're on the other side. Well, I'm just going to do second entry because the only thing that changed is the distance we are away. Instead of 2,500,000, we are 12 million, right? 12 times 10 to the 6th. So 12 times 10 to the 6th. So 12, 1, 2, 3, 4, 5, 6. There we go. So that gets me negative 3,335,0,0,0. Okay. And what this tells us, right? This is a smaller absolute value, but it's negative. So this actually means we have more potential energy of gravity at point B, which is further away. That's what we're going for. So negative 1, 2, 3, 4, 5, 6, 7. 3.335 times 10 to the 7th. Negative 3.335 times 10 to the 7th. Then one last term that we have, and that is this 1/2 times 3,000 squared. So 1/2 times 3,000 squared. All right. So we have this. How many decimal points is that? 1, 2, 3, 4, 5, 6. 4.5 times 10 to the 6th. So plus 4.5 times 10 to the 6th. Okay. So let's take some of these numbers here. Let's run this calculator over to the other side. So we have negative 3. Negative 3.335 times 10 to, oh gosh. Sorry, my calculator is not wanting to be nice to me this morning or this evening. We have this number plus this number. That's what we get on the right side, is we get that. But then we have to add, right? We have to add this 1.6008 times 10 to the 8th. We're going to add that. Right now it has it as a negative, so I'm just going to go ahead and delete that negative sign. Add that together. Okay, that's the number we get. So we have 1, 2, 3, 4, 5, 6, 7, 8. 1.31 times 10 to the 8th. So 1/2 velocity of a squared equals 1.31 times 10 to the 8th. Right, times 2, and then square root the whole thing. That'll just get us the velocity. So our velocity of A times 2, and then to square root the whole thing to the 0.5, that gets me 16,200. 16,200 meters per second. All right, there's our velocity at point A. That's our velocity. So this shows us, right, in an elliptical orbit that moves moves. Right, this is a fair assessment of a satellite moving around the Earth. But in this orbit, where it gets a lot farther away at this point B, it's a lot further away from the Earth than it is at point A. So it has to be moving a lot faster at point A because of this conservation of energy. If we decrease the gravitational potential energy, right, we bring it closer, we have to account for that energy elsewhere. We have to increase kinetic energy. All right, so there's that front page. Let's go to the back side of this page. All right, same question, same setup. Okay, so we've got, which of these graphs best represents the strength of the gravitational field caused by Earth at the location of the satellite as it orbits? Briefly explain your reasoning. All right, okay, so we've got 3 options here, 1, 2, or 3. The strength of the gravitational field, is it going to be positive or is it going to be negative? Okay, well, we've got this over here. That's a flat line. Is it positive or negative? Well, we don't really know the answer to that necessarily. But is it going to be a flat line as we go from Earth and then orbit around it? The strength of the gravitational field. Well, is gravity going to be equal at this distance and at this distance? I hope you'd say no, and that is correct. No, the gravity is not the same at those two distances, right? We get further away, gravity gets weaker. We don't have a big gravitational pull toward Jupiter, but we do have a pretty decent gravitational pull toward the moon or toward the sun, is just because it's so massive. Okay. So which of these best explains it as it moves around? So if we're at point A, let's think about this. If we're at point A, is our gravity going to be large or small? All right, we're close to the planet at point A, and I should really do this over here. We're close to the planet at point A, and we're far from the planet at point B. So is our gravity going to be large or small at point A, where we're close to it? Well, it'll be large, right? If we're close to the Earth, it'll exert a lot of gravity. So I'm going to go with graph 2. Graph 2. Right? If we are close to Earth, which happens at point A, right? When we're close to Earth, which happens at point A, that means that we will have a lot of gravity. So gravity will be large. Gravity will be large. But if we are far from Earth, right, the farther we are from Earth, which happens at what point? At point B. The farther we are from Earth, gravity is small. Gravity is small. So it makes sense that we need to have the smaller number at point B and then the larger numbers at point A. Okay. Then part G, which of the above graphs represents the total mechanical energy of the satellite Earth system as it orbits? Remember, total mechanical energy, that's just energy total. So that's going to be our kinetic energy, gravitational potential energy, and then potential energy of any springs that are involved. Well, the satellite, there's no springs in there. So it's just going to be kinetic energy plus potential energy. But if you remember this, right? Energy initial plus work equals energy final. What did we say about work? Is there any work being done on or by this satellite? No. So we know that the initial energy has to equal the final energy. It must be the same at point A, at point B. It has to be equal. What's the only one of these graphs that is equal the whole way around? Graph 1. That is the only graph that is equal. Okay, so this means that this one's going to have to be graph 1. Has to be graph 1. Because energy must be conserved. Energy must be conserved. Since there is no work being done, right? No work is done because there's no outside forces, which means that the total energy, right? Total energy cannot change. The total energy cannot change. Okay. So that's a wrap on that problem, actually. That's a full AP level problem. And that'll do it. All right. Number 2 now. Number 2. We have a rocket continuously firing its engines as it accelerates away from Earth. For the first kilometer of its ascent, the mass of fuel ejected is small compared to the rocket. For this distance, indicate the changes, if any, to the kinetic energy of the rocket, gravitational potential energy, and the mechanical energy of the Earth rocket system. Okay. So the kinetic energy, right? Kinetic energy, are we getting faster? Are we getting slower? Or are we staying at the same speed? Well, let's read the problem closely. As it accelerates away from Earth. Accelerating means, well, it's getting faster. So what does that do to kinetic energy? Increases. So kinetic energy increases because the rocket is accelerating, right? So it's moving faster. So that means velocity is increasing. When velocity increases, And note, right, because kinetic energy, 1/2 mv squared. It says the mass of the fuel ejected is small compared to the mass of the rocket. So that means mass doesn't really change all that much, but velocity does. It accelerates. All right, gravitational potential energy, well, mgh, right? Or if we're going to think about it in terms of big space gravitational potential energy, gmm over r, negative gmm over r. Well, if we think about it either way, right? Mass stays basically constant. I know G doesn't quite stay constant because our rocket is moving so much and so fast. But H is increasing. H is really increasing. If we think about it in terms of this other one down here on the bottom, right? Negative G, that stays constant. Big M, right? That's the thing causing the gravity. So that's the Earth. This is now the mass of the rocket, which stays essentially the same. And then R. Well, as R increases, we go from small r, so a big negative number, to a little r as we get higher and higher, right? Higher and higher as the rocket is moving up. So, right, here's our rocket. I'm terrible at drawing rockets. Absolutely terrible at drawing these rockets. I think I know how to draw the rocket. Here we go. So there's the rocket. Woo. There's all that. Sorry, I don't mind my cat helping me make rocket noises. Okay. So there's our rocket, right? And there's all the fuel coming out of the back. And there's the Earth down below. So as we increase our radius, right, we go from a really when r is small, we have a big negative number, so it's really negative. But then as r gets bigger and bigger and bigger, then we get to a smaller and smaller negative number. So we are increasing that number, which means gravitational potential energy increases. Right? We can tell that because we are moving farther from Earth. We're moving farther away from Earth. And that's really all you need to know, is that when you move farther away from Earth, potential energy of gravity increases. All right, total mechanical energy. Last question now. Well, kinetic energy increases, gravitational potential energy increases. We know that total mechanical energy, right, that's going to be our potential energy of gravity plus our kinetic energy plus any potential energy of any springs, but there aren't any involved. Well, this increases and this increases. So what does this one have to do? Well, that's going to increase by a lot. That'll increase by a lot. So this will absolutely increase, right? Because KE increases, and potential energy of gravity increases as well. And that's it. That's really all the explanation you need. All right, so there's that second question. There's the whole worksheet. If you have any questions, please let me know. Otherwise, good luck on this. Hope you were copying this all down as you went through, but make sure you understand it. Make sure you can replicate it if I ask you again. All right. Well, I will see you next time in class. Have a great rest of your day.